Hello everyone. This is my first homework exercise from the course of Computer Systems Architecture from the ADA University. In this presentation, I'll try to describe how computers realize comparison operations in hardware level. Unlike to the software level, especially in high-level programming languages, there are no special types of comparison operators in hardware level. Without having special types of comparison operators, how do computers realize comparison operations in hardware level? Actually, answer is simple. With the help of subtraction and some logical operations. But before going direct solution and calculations, let me introduce you some related concepts. Concept is about representing positive and negative numbers in computer memory. There are two main ways of representing numbers in computer hardware. The first method is called unsigned representation, which allows you to represent only positive numbers in computer hardware, but with simpler way. With the help of n bits, you can represent to the power of n integers in computer hardware. And range starts from 0 and goes to positive n power of n minus 1. In the example, I have shown that with the help of 8 bits, you can represent 256 integers in computer memory. It can start from 0 and goes up to 255. But what about negative numbers? Unfortunately, unsigned representation doesn't allow us to store negative numbers in computer memory. To represent both positive and negative numbers, we use a representation which is called signed representation. It allows us to represent for the number of n bits from the range begins from negative 2 power n minus 1 to positive 2 power n minus 1 minus 1. In the example, I have shown that for n equals to 8, we can store numbers from negative 128 to positive 127, which includes 0. To represent signed integers, we can use different methods. Some methods may demand additional hardware to handle negative numbers, but there are alternatives which don't require additional hardware. Some of them is called ones complement, but better approach is twos complement method. In twos complement method, negative values can be represented with the help of two operation. One of them is inversion and another one is addition. The importance of this method is we don't need additional hardware to handle negative or positive sign. We just take a number, positive number, we inverse it and we add 1 and we get negative representation in signed number, as a signed number. In the example, I have chosen 5 to represent negative version of it. For simplicity, we use 8-bit register here, but in real case, register size might be bigger in real architectures, but for simplicity we use 8-bit registers. In the first 5 digits, all are zeros, and as representation of 5, we use 1, 0, 1, and we inverse all of these digits, including empty digits like first 4 zeros, and we get 1, 1, 1, 1, 1, 0, 1, 0. And we just simply add 1 to this result, and we get 5 ones, 0 and 1, 1. This is the representation of positive 5 in a negative way with the help of twos complement method for signed integers. But how do we know the given binary representation of integer is positive or negative. To know this, in this case I have given the two binary representation of the same integers. They only differ from their sign. In the first case, the first digit is 1, and in the second case the first digit is 0. These first digits are called the most significant bit for each. If the most significant bit is 1, it means that this signed integer is negative, and otherwise it's positive in case of 0. But this rule works for signed integers. In unsigned integers, there is no representation of negative numbers. Therefore, if it is 1 or 0, it doesn't matter. This value is positive. But why do we need that? As far as we know, we can't directly compare each number, two numbers in hardware level. We do that with the help of subtraction and some logical operations. In the next slides, we'll see that the help of the most significant bit is important to compare two integers in hardware level. Before doing comparisons, another important concept to learn is overflow. Again, this concept is important for signed integers. In this example, I have chosen this 8-bit representation of 64 for addition operation. As a result, we get 1 and 7 zeros in this case, but it is wrong for signed numbers because we change the first significant bit, and it means negative 128, and it's called overflow. This concept is important because we'll work with some flags which helps us to learn how to compare two digits in hardware level. So far, we have learned some concepts like representing positive and negative numbers in computer memory, the most significant bit, and overflow. Now it's time to learn about NZCV condition flags. NZCV condition flags is related with ARM computer architecture. ARM computer architecture is a group of RISC computers which works fine with portable and mobile devices. And ARM architecture works with registers. These registers are grouped for different purposes, but we are interested in group of status registers in this case because it keeps NZCV flags or NZCV bits. But what does NZCV stands for? In this case, N means negative, N means negative, Z means 0, C means carry, but it's for unsigned group of numbers, and V means overflow for signed group of numbers, as we know. The importance of NZCV is related with the arithmetic operations on CPU. On CPU, if any arithmetic operation comes up with negative value, in this case N bit becomes 1. If the result is 0, Z bit becomes 1. And if there is a carry for unsigned operations, the C flag becomes 1. To explain carry, it's related with the addition operation, for example. In the case of 8-bit registers, if we sum up two binary representation of integer values, and if it demands extra space for generated bit, and if there is no room for this bit, it becomes carry, and it rises carry flag. And for overflow, in case of signed integers or signed numbers, there is V flag which can arise. NZCV condition flags are important to compare comparison operations, and we'll see that in upcoming slides. Now it's time to look at comparison of two numbers. For this purpose, let's divide these comparison operations to 4 categories. The first category is greater than or equal and can be represented as GE. And second one is LT, which means less than. The third one is GT, greater than. And the last one is LE, less than or equal. Let's go one by one and let's see which flags are important to calculate comparisons of two numbers. Let's begin with greater than or equal. In this case, to tell the greater than or equal condition is true or false, we have to check two flags, negative and overflow flags. If both of them are equal, we can say that the condition is true, otherwise it's false. For example, in this case, for true condition, I have chosen 5 and 3 as comparison integers. As far as we know, we can't directly do comparison in hardware level, and we do that with the help of subtraction. We subtract these numbers and we get a result. In the result, we have 6 zeros, 1, 1 and 0, which represents 2. And as we see, there is no negative flag because the most significant bit is 0. And it makes it obvious that negative flag and overflow flag is 0. And this means equality. In other case, we subtract 7 from -5 and we get result. Here negative flag is 1, but overflow flag is 0, because in the overflow case we have to come from 0 to 1 as the most significant bit. But in this case, the most significant bit from -5 was 1, and after subtraction it's still 1, and it doesn't break overflow. And in this case there is no equality, and it means this condition is false. -5 is not greater than 7. Now look at less than case. We can say that less than is the opposite of greater than or equal case. And it means that we have to look at N and V flags again, but in opposite way. For example, to say that greater than or equal case to be true, we have to say that N and V flags must be equal. But in less than case, we have to say opposite. It means that to be true, N and V flags must be unequal, and to be false, N and V flags must be equal. Let's look at example. In the true case, we try to compare 3 and 5. Is 3 less than 5? To say that true, in hardware level, we have to subtract 5 from 3. And we get 1 as the most significant bit. And it means that negative flag arises. But there is no overflow. To make sure overflow happens, there must be no space for sign bit, and this is not the case, and it means this case is true because negative and overflow bits are different and they are not equal to each other. And let's look at false case. Now we try to compare reverse order. We try to compare is 5 less than 3. To be sure, we first subtract 3 from 5. And we get 0 as the most significant bit. And there's no overflow. And both are equal. In this case, we can say that the condition is false, because to be true, n and v must be different, and this is not the case. Now it's the greater than condition. To check whether one number is greater than another, we have to look at 3 condition flags. Again, n and v, but additional to that, we look at z flag, because z flag gives us information about the equality of compared numbers. If numbers are equal, we can't talk about greater than relationship between them. And therefore, z must be 0 and n and v should be equal to each other. Let's look at examples. In the true case, we compare that is 6 greater than 2. First we subtract, and as a result we don't get zeros, and that means z flag is 0 because there is no equality between numbers, and the most significant bit is 0, and it makes n 0, and there is no overflow, and v is 0 again. N and v equals to each other, and z is 0, and this satisfies all conditions, and it means that 6 is greater than 2, and this condition is true. In the false case, we compare same numbers, and as a subtract we get all zeros, and it makes z flag to 1. And there is no need to check another case which is related with n and v, because already condition isn't satisfied, and it's false case, and this is greater than condition. And we come to the last comparison, which is less than or equal. And to check this condition, we again look at n, v and z flags, and if n and v flags are unequal or z is 1, it means that this comparison gives true result. This condition is true. We don't need to check both of them. If one case satisfies the condition, it's enough. In the examples I have given all cases, I mean less than case, equal case, and a general false case. And let's look at each of them. In the first case, we try to subtract 5 from 3, which means that is 3 less than 5, and we get different n and v. And it means the first condition, n and v must be unequal condition, is true. Therefore, there is no need to check z must be 1, and it's always if one number is less than another, there's no need to check equality. In the second case, it's easier to check equality, and we see that z is 1, and it satisfies the general condition, and general condition is true. The third case, we check z is 0, but it's not enough to say that the condition is false. We should check n and v and be sure that they are same to say that this condition is false. And we see, as the result of subtraction, there is 0 in the most significant bit, and it means that n is 0 and v is 0, and they are equal. And we can say that 3 conditions are not satisfied, and general condition is false. And that's all about my presentation. I try to give brief information about comparison operations in low-level computer hardware, and thank you.